So in a previous lesson, I talked a little bit about what the inverse of a function actually is, if that function is one-to-one. So this lesson is going to be about going ahead and then finding that inverse. So just a little refresher, what the inverse is going to do is if your function maps x to y, then the inverse function is going to essentially undo that, and it's going to send that y right back to the original x. So yeah, what's happening is if on the function we have this point x and y, then on the inverse function, we're actually going to have the flip of that. We're going to have the point yx, y maps to x. So the name of the game is going to be basically flipping x and y every single time. So we'll do the three different styles of function representations. First one's just a collection of points. The first one, I'm telling you, it's an invertible function. You should be able to double check that if you don't trust me. And all we're going to do is go through and yeah, flip it around. So yeah, we have just nice invertible function. I'm going to take every point and then just swap the xy in every single coordinate. So I'll have 1 and -3, 2 and 0, -1 and 1, and 3 and 4. Yeah, so those cases are pretty straightforward. Yeah, you just flip everything. You'll see that the resulting expression is a function. We wouldn't have had that if f was not one-to-one, but it was, so it all works. And yeah, we're good. All right, the second example, what I've got here is a graph. So if you remember, you'd apply that horizontal line test to check whether or not this thing is actually one-to-one. And if you draw any horizontal line, you'll see that it only intersects that picture once. So it is one-to-one, which means it has an inverse. And so yeah, we can follow that approach of flipping your x's and y's. We could use that if we like to maybe find a whole bunch of new points. So what we might want to do is actually label a bunch of points on here. So this point here, that little corner, is at -1 and 1. I'd have a point right here at -2 and 0. And if I follow that pattern, it does look pretty linear. -3 and -1, and maybe I'll just draw one more down here. And that looks like -4 and -2. Maybe my line's not perfect. I'm going to jump over by 2 because that's what my slope kind of suggests. Here I've got a point at 1 and 2, and then maybe a point at 3 and 3. And it looks like this last point would be at, well, my scale's not great, but it looks like 5 and 4. And so yeah, what we would do is actually just flip all of those coordinates to get a whole bunch of new points. So I'll draw the flip maybe in green. So -4 and -2 is going to come to -2 and -4. And -3 and -1 will be -1 and -3. -2 and 0 will be 0 and -2. Is that right? Oh, no, my last point doesn't appear to be in the right place. Oh, I see. My problem is the first point is definitely not in the right place. I might be able to move that. Let's see how this works. Yeah, sorry, I drew that one a little too low. So that should be better. Yeah, it's looking like a line now. That's what I want. Yeah, so -2 and 0 goes to 0 and -2. -1 and 1 is going to go to 1 and -1. And that was a vertex there, so we will start to see a little bit of a different behavior as I flip this around. 1 and 2 is now going to go to 2 and 1. And you see that point now is not falling on my line at all, so that's going to sort of create a different branch. I want that to come out a little thicker. There we go. And I'll keep going with a few more points. 3 and 3 is going to stay right at 3 and 3 when I flip the x and the y. And 5 and 4 is going to go to 4 and 5. And you see those mostly look like they're going to also fall on a line. Kind of. I'm going to try and fudge it a little bit. And we would assume that pattern would keep on going. So what we end up getting is this new function here. That is going to be my inverse function. So that'll be y equals f to the -1 of x. And what you'll actually notice if you look at this drawing is it's actually a mirror image. And so you can use that as a shortcut if you like to draw any of these. Let's find a new color. And what I'll do, is there a dotted line option? There is not. No. Yeah, so if you actually look at what we've got here is it should be pretty much a perfect mirror image over the y equals x line. Or your 45-degree diagonal. Now, if you tilt your head, you should be able to see that. It actually looks pretty good, all things considered. Yeah, so especially if you have any like curvy bits to your curve that you're trying to transfer over to this inverse, instead of doing a whole bunch of points, because it's maybe really hard to figure out what are the key points when it's curvy, this mirror image trick will work much better. You can probably draw it a little bit freehand, but I do still recommend tracing a few points over, like x to y, y to x, and that should work a little bit better for you. But the blue one is our finished product, and that would be the graph of your inverse function. Yeah, and it's coming directly from what we did in the first example, just taking the points, flipping the coordinates. And the reason why we do that is because, for example, -3 maps to 1, and we want 1 to map back to -3, so it cancels. All right, finally, we will talk about the explicit case. So let's go with y. No, not y. I'll use the f of x notation. All right, so what we've got here is this function f of x is 2x plus 1 over x minus 3. I'm not going to draw the graph of this, or I'm not going to draw the graph of it. If you look up a Desmos graphing, I'll write that out for you if you want. It's a nice handy tool. But yeah, so if you Google that, you'll get a nice graphing simulator that you can just plug things into, and I'll show you what the graph looks like. So you can kind of cheat on a lot of the problems we'll do in this course with that, but it's handy. I'll show you what the graph looks like, and you'll see that it will pass your horizontal line test, which is nice. For us right now, our test to see if this thing is actually one-to-one, normally, if I asked you to find an inverse, you could just assume that it's one-to-one. But the test is basically half of the work. So what we'll do is start with the test. So what I'm going to do is swap out the f of x for y. So we'll have y equals 2x plus 1 over x minus 3. And then if you remember, what you do is you actually check to see if x is well defined in terms of y. And so in order to do that, we solve for x. And so, yeah, solving for x is a little bit tricky here. Step one, what you might want to do is make it linear. So we've got division of x's in here. So right now it's a rational equation with regards to x. I don't want that, so I'm going to make it not rational. I don't want division. I'm going to get rid of it. So I'm going to times both sides by x minus 3. So essentially what that will do is bring my x minus 3 up to the left-hand side. So I'll have x minus 3 times y equals 2x plus 1. And pretty naturally, I'm going to simplify the left side. Yeah, so this is what we get here. I'm still trying to solve for x, but you'll notice that the problem that I'm running into right now is that I've got two different x chunks. So what I'm going to do is bring them together. So I'll maybe subtract the 2x onto the left side. And then I'm going to move the 3y. I'm going to move everything that doesn't have an x over to the right-hand side. And so what that's going to allow me to do now that these two terms both have an x, I can actually factor the x from the left-hand side. And so what I'll get is x times y minus 2 equals 1 plus 3y. And now I can actually solve for x. I get 1 plus 3y divided by y minus 2. And that's well defined. If I know what y is, I just plug it in and I get one output for that particular y. So that is exactly what I'm going for. And that means that f of x is invertible. It's 1 to 1, so it's invertible. And so to actually do the inverse, all we do, just like the other ones, is swap x and y. So I'm literally going to turn all x's into y's and all y's into x's. Just a swap, just like what we did with all those points. And what we end up getting is y equals 1 plus 3x over x minus 2. And that's it. That's my inverse function. So that's my inverse. So I'll just finish that last step. We're going to write it as the inverse with the correct notation. And yeah, that should be it. And now this one, it doesn't look as obvious as some of the other ones where it's just like compute a few operations and then the inverse looks like undo those operations. This one's a little bit more complicated. So that is the final answer. It might be worthwhile to actually go through and maybe do a check. So I guess I'll choose another color here. So we can do a check if you're not convinced. So what we'll do is maybe just verify that f composed with f to the negative 1 of x is x. So if I plug in that f to the negative 1 of x, so that function that I just found into my f, I'm going to get f of 1 plus 3x over x minus 2. And I'll just keep working this out. So that'll be 2 times the inside plus 1 over my inside minus 3. And hopefully this does all work out. Otherwise, I have to go back and fix all this. Yeah, so what I'm gonna do to clean this up, to me, instead of yeah, we got fractions and fractions, which are kind of ugly. So I'm gonna save a little bit of time here. And I'm gonna multiply the top and the bottom by x minus 2 with the goal of canceling out that x minus 2 in the first term, right? Both the top and the bottom are broken into two terms. One of them has an x minus 2 on the bottom and the other one doesn't. So the nice thing is it'll just cancel that one, and then the distribution through the second term isn't overly complicated. So yeah, so what I'll get is 2 times 1 plus 3x, and then plus 1 times x minus 2. So that's when I distribute the x minus 2 across. And then the bottom, my 1 plus 3x is left over because the bottom's canceled, and then minus 3x minus 2. And I'll just clean all of this up. So on the top, I'm going to get 2 plus 6x, and I distribute the 2, plus x minus 2. And then on the bottom, I'm going to get 1 plus 3x minus 3x plus 6. And something looks a little wrong there. Maybe I can catch it. Oh, no, okay, no, it looks good. It looks good. I was stressing out a bit. Yeah, so we can see those 2's cancel. The 3x's cancel on the bottom. So what I've got when I combine the top is 7x over 7. That 7 was throwing me off, but it's okay. Those cancel, and we're actually just left with x, and that's the thing that we want. So it all checks out. Yeah, those rational inverses are a little wacky looking. But this worked. This technique worked. I generated a thing that actually is my inverse. So yeah, that's how you'll do it in general. And these probably algebraically are the hardest ones that you would come across. Typically, it's just like cancel, cancel, cancel.